Hello, I'm Umnik. I'm a bit late to the party, but I'm going to solve the second division universe round 1007, and I'll try to explain what I'm doing. So I guess that's what they meant by 6 or 7 problems. 6 with subtasks. Okay. Problem A. Okay, we have some 2-player game. We have 3 players. In each match, 2 players compete while the third spectates. To ensure fairness, no player can play 3 times in a row. So they basically rotate. Right? If first and second play, then first and third, then the first must not play, so it's second and third, and they rotate. Okay, the player who plays twice in a row must start as a spectator in the next match, which will be played by the other 2 players, otherwise the winner and the spectator will play in the next match, while the loser will spectate. So that matters only for the first match. The player is fully immersed in this infinite loop match. It has task with one problem. Whether the spectator of the first match can be the spectator in the case match. So that basically just means, is it true that k mod 3 is 1? Right? Looks like it. I mean, I think I have proven it, right? The first and second place, third spectates, then let's say the first stays third place, but then the first must spectate, then the third must spectate, the first must spectate, then the third, then the second, and so on in a loop. So the third spectates if and only if k mod 3 is 1. Problem B. Have a permutation that's called perfect. For each index, the prefix sum of first I elements is not a perfect square. So the permutation is perfect is the prefix is not. Okay. Construct permutation of given size. Wouldn't just 1, 2, 3 and so on and almost work, except 1 is bad. That must be true, right? So the sum of numbers from 1 to k is a case triangular number, and it cannot be square unless it is 1. And so to get the answer, we just swap 1 and 2. Make sure that the first prefix sum is not in a square, and then all the others will be triangular numbers. I mean, it's faster to just check, even faster to just submit, but let's try to prove it. So I want to prove that for all n that are at least 1, n times n plus 1 over 2 is not a perfect square. Probably I want to try from contradiction. Let's say that it is. And at least 2. Sorry. Multiply by 2. How do I prove that? It must be true that if I take square roots of both sides, this is slightly greater than n, probably close to n over 2. I mean n plus 1/2. And this is m times square root of 2. But that doesn't really prove anything. I'm sure that me 15 years ago would know how to do this. Maybe it's not that easy actually. Okay, that's just not true, right? 8 times 9 over 2 is 36, which is 6 squared. Okay, that was easy. Interesting. So for n equal to 8, it is not possible. That's fun. Are there any other counterexamples? I don't think that it should be possible for a lot of numbers. Right, like 120 is a triangular number and it's almost 11 squared, but not exactly. Okay, if it's not true that it's not always possible, then I should probably try to just solve the problem some way. So the perfect squares are kind of rare, so maybe just try and random permutation would work. But I think that probably my original idea is like more or less good. So let's start with any permutation. For example, the identity permutation. But probably okay, well, with identity permutation I think I can explain why it works. But I think it should work like with any reasonable choice of permutation. So what I'm gonna do is, like, we want to calculate prefix sums and then make sure that none of them are perfect squares. And actually I can try to make sure that they are not from like any given set that is sparse enough, and I think I only need actually okay, that's not obvious. But okay, what I want to do is let's look at some prefix that is bad. So we know that this prefix is bad. The sum of numbers from 1 to 8 is 36, which is a perfect square. We don't like that. How to fix that? I'm saying let's swap those two numbers. What will happen after we do that? Well, I state that we will not change any prefix sums except this one. Because for all prefixes except like up to this point, the set of numbers on the prefix did not change, so the sum also did not change. But here we swapped those two numbers, so I decreased the prefix sum by this number, but increased by this one. But since they are different, like my prefix sum cannot stay the same for sure, and also since they're close, actually they differ only by 1, when I swap them, I just increase the prefix sum by 1, and that surely makes, like, if I had a perfect square there, now I don't have a perfect square because I have some perfect square plus 1. There is a slight issue here. The issue is that if I have two consecutive prefix sums that are bad, like I can do the first swap, but then on the second swap it is not true anymore that they only differ by 1, they will differ by 2, which is still okay for our purposes. But if there are a lot of such bad prefix sums in a row, then it might break. Sorry. I have a very diligent doorman, or rather door dog, that announces all the post brought to our apartment. What was I saying? Right. So if I have a lot of bad prefix sums in a row, to fix all of them, I will, like, if I will do the swaps consecutively, it might still be bad. It might happen that after the swap, the new sum is also a perfect square. I think that in this particular problem, when our band set are perfect squares, it is not possible. Probably because the only bad prefix sums will be 1 and 8. I still believe that, like, it shouldn't happen a lot, or at least I think it shouldn't happen on, like, big numbers, because that would imply that like there are very good like rational, well, not really, but something close to, like, it would imply that there are good rational approximations of square root of 2, which there are, and like, I'm guessing that, like, 8 and 6 are one such approximation, or rather, I guess it should be like 8.5 and 6, so like 17 over 12 is a good rational approximation for square root of 2. That's correct. Like, if we take square of z, that would be 289 divided by 144, which is, like, very close to 2, like, right? It's 2 and 1 over 144. And there are good rational approximations of square root of 2. but I don't think that they're like that good in general. Although, like, I'm not sure anymore. What if we take the next one? The next one should be like 2964. No, the other way around. But I need 2917. I need okay. I need an odd number here. So the square of that is okay, so that didn't work. Why that didn't work? Probably because I'm doing something wrong. Whatever. I don't remember how to find good rational approximations. It's not very important right now. But in any case, I'm sure as hell that there won't be two consecutive prefix sums that are bad, that are perfect squares. That I should be able to prove, right? The gap between squares is bigger than the gap between triangular numbers. So if I have a triangular number that is a square number, the next triangular number will be strictly less than the next square number. So this bad situation should not happen. Thus, like, all my bad prefixes are at least on distance 1 apart, but I think that, like, this should happen very rarely. And so, like, with swaps, I can fix all of them except maybe the last one. If, like, my whole sum of the array is a perfect square, I cannot do anything about it. But, I mean, there is no element to swap with, but also I cannot do anything about it because, like, my array must consist of numbers from 1 to n. So if n times n plus 1 over 2 is a perfect square, I'm screwed. Like, there is just nothing I can do. Okay, that took a lot of time. Well, whatever. Hopefully it was somewhat educational. So our solution is to take identity permutation, go left to right, calculate prefix sums, and if a prefix sum is a perfect square, I want to swap two elements to fix this prefix sum. And if the sum of the whole array is a perfect square, just print -1. We cannot do anything about it. I'm rather interested what is the intended solution and whether, like, just taking random permutation works. I mean, it probably shouldn't. Even though perfect squares are rare, like, we should have none of them. But I guess okay, I think that, like, you should get a good permutation with constant number of tries if it is possible. So yeah, just taking random shuffle 10 times should work probably, or maybe, like, not 10 times, but like, check that the sum is good and then take random shuffle until everything is good. And it's not that easy to implement, actually. Like, I need to check that something is a square fast. Like, one way would be to just calculate all squares and throw them instead. but I can try to like extract square root and check that it is an integer, which you need to do carefully still. So when I want to get a square root rounded down of a number or something of that sort, for example, like check if the number is square, what I do is take square root with built-in function in doubles, but then I will always write this while that like fix the value, because this might be calculated not precisely. Our numbers are up to like 10 to the 12th, which should be good enough, except like if the number is actually an integer, like square root will be also like an integer, but maybe it is calculated a bit not precisely, like, and it's a bit smaller than the actual result, and then this will round it down, and we will get result one less than needed. I don't know like what is the smallest number on which it happens, but it can surely happen. So if you want to take like square root in integers, you can write binary search, or you can do something like this. Use doubles, but then find the actual correct result by increments and decrements. What? Okay, I'm not great at checking if something is a square. Oh, right, because after the swap, I'm adding the numbers. Okay, that's stupid. So yeah, I guess I should rewrite it. That is still wrong. What is going on? Okay. if it's not pretest passed, I will go insane. Also, yeah, I'm interested, like, if it happens after 8. Yeah, there are a lot of them. Well, not a lot, but yeah, I guess those are like good rational approximations of square root of 2. So that's great. Yay, it works. Okay, let's forget about that. Problem C. We're given a tree and a permutation. There are n steps. For each step, tempting piece of Parmesan cheese appears at some vertex. The mouse is currently at vertex pi. It will stay there and enjoy the moment. Otherwise, it will move along the simple path by one edge. So, like, there is a mouse on the tree. It starts somewhere, and then we activate vertices by one by one, and in some permutation order. So each vertex is activated exactly once, and the mouse will move one edge closer to the activated vertex, or just stay there if it's already there. The task is to find such permutation so that after n steps the mouse inevitably arrives at vertex n where a trap awaits. So we're given a tree, starting vertex and ending vertex. The mouse starts in the starting vertex. Then we need to activate vertices in some order that we choose, so that in the end the mouse will be in the ending vertex. That's interesting. Sounds like a cool problem. Don't even know like how to start. There is an option to print -1, but no -1 in samples. Well, it seems that it should be always possible, right? We have a lot of freedom, and like, it kind of feels like we should somehow spend all the moves that are useless and then just lead it like to the end one by one. But how exactly to do that? Unclear. Okay, I think I want to do something like, let's root the tree at the target vertex, like where I want to arrive. Let's say I start here. I want to do something like this. I want to use this whole subtree and make sure that at the end I will still be at this vertex. How to do that? Guess for so I have a subtree. There is some path to the root, and I can do like the following recursive function with this subtree and starting either in this subtree or in this path or one step away from it. This is path to the root. I want to use all the vertices in this subtree, and in the end I want to be on this vertical path from the root to the root of this subtree. How am I going to achieve that? So if my starting vertex is in one of the subtrees, so like this is my root, it has a lot of suns, and let's say that starting vertex is here, and this is path to the root here. I can call this function recursively from this subtree. The starting condition holds. This vertex is in the subtree. And so the recursive function will make sure that I will arrive somewhere on the vertical path to this point. But obviously I cannot go outside of this subtree, so I will arrive here. And then for every other subtree of this vertex, I can also call the recursive function, because this vertex satisfies the starting condition. Like it is on distance 1 from the vertical path to the root of this subtree. And so in the end I will make sure that it is on the vertical path. Once I do it for all the subtrees, my current vertex is either one of them or somewhere on this vertical path. And when I activate this vertex itself, if it was in one of the suns, it will go here. If it was on the vertical path, it will go like one down on the vertical path, but still it will stay on the vertical path. Okay, that's if I started inside. If it started outside, then like it doesn't matter. I can just activate the subtrees in any order. So yeah, basically if I am inside, then I need to first activate well, actually it shouldn't matter. Like I cannot do anything wrong. Okay, I cannot do anything wrong. That's a strong statement. Okay, so I guess the following solution should work. Start like so there is target vertex, run BFS from it, and basically we assign for each vertex its height in the tree rooted by the target vertex, and then activate the vertices in the reverse order, so like from the lower levels to the higher levels. I want to prove by induction that if I just activated some vertex u with height h of u, then I'm at vertex v with height not greater. So at any moment the current height of the vertex I'm staying at is not greater than the height of the vertex I just activated. I want to prove this by induction. After the first activation, it is true because the first vertex I activate is the lowest vertex possible, so it has the largest height. So I'm at some vertex in the tree, and the height of that vertex is at most the largest height of any vertex in the tree. So that is true. What happens like after I activate some vertex u? So this is u. What are possibilities? I can be like somewhere below. I can be somewhere higher. I can be like somewhere else. So like if I'm here before I activate u, so like what is the option? Basically, what is the LCA of this vertex and u? Is it u? So we are somewhere under u, like inside its subtree. Is it this vertex? So we somewhere higher, or is it some other vertex? So it's something like this. So what will happen in any of those options? If we are in the subtree of U, so somewhere here, we will go one higher. But by the induction hypothesis, we know that our height was not greater than the height of the vertex we activated just before this, and that cannot be more than height of U plus 1, because like it was the next vertex in order by height, and like we cannot jump through the height. So the height of the previously activated vertex was either the same one or one greater. So we were like on this level, or like somewhere higher than this level, surely. And if we go up, then we surely will be not lower than the level we want. If we are somewhere here, like LCA is some other vertex, we will also go up, right? In the direction of U is here. So we'll also go up, and the same is true. And if we were on this vertical path but not in U, we will go down towards U, but we will still be not lower than it. So I have proven this statement by induction, and if I do all of that, at the end it means that the height of my current vertex is at most 0, so I'm at the root, which is what I wanted. So the starting vertex doesn't matter at all. We just root the tree at the end vertex, order them in the decreasing order of height, activate them in this order. That's the answer. Oh, like that's one of the answers. It's one of the possible answers. That is super cool. Okay, I love this problem. Okay, let's write that. It is a tree, so like DFS, BFS, it's all the same. I think it's just easier to write BFS. I don't even need like use. I don't need distances. I can be okay with just use. I mean, it's always true for BFS, but like, I mean, I don't need the actual distances. I just need the order. Yeah, sorting by the order of distances is just use the order in which we traverse the vertices in BFS. So sorted by distance is BFS order. And just write BFS from the target vertex. We will not use starting vertex in any way. Just write BFS. I need to mark used. and then output the vertices in the reversed order, because I want to go from leaves to the top to the root. Okay, I'm printing some other answer, but that's fine. That is absolutely amazing. Problem D, easy version, infinite sequence. The difference between the versions is that in this version L is equal to R. Okay, you are given a positive integer n and the first n items of an infinite binary sequence A, which is defined as follows. So we're given first n elements, and then for all greater it is a XOR, the prefix XOR of length half. Okay, the task is to compute the sum of elements in a given range. So in the easy version the range is of length 1, so we just ask to find one element, and I guess in the hard version it is a segment. Okay. Well, that doesn't sound too hard or too interesting. So we are given first n elements. Let's also find the next n elements. Now after this, like we will always take this prefix. So okay, the 2n plus first element is still XOR on this prefix, and then every two next elements will have like this next element included, and then the next one, and then the next one, and so on. But the thing is that we generate elements in pairs, right? So like if those two indices have the same result of division by 2 rounded down, then their values are the same. So when we take XOR of both of them, they will cancel each other out. Right? So but that doesn't really help us. Interesting. But I guess I still want to use the fact that like, pairs of consecutive elements are the same, and like okay, what are the limitations? 10 to the fourth. Okay, I think it can be done in logarithm time, but like log square is fine and it is easier. So let's just do log square. Okay, first I still need to solve the easier version in logarithm time. So let's just write a function f of x that will return like how to do that. If x is at most n, we just know the answer. Otherwise, we know that the answer must be a the prefix SOR of size x over 2, and if it is small, then again I can just take the prefix SOR. Otherwise, I say that okay, I need to take prefix SOR here. But actually, like all my elements, so I have like first n elements. I guess I need to make n odd. So if it is even, then I will just like find the next element and say that it is also given. So I have the first n elements, and then all the other elements are split into pairs of equal elements because they were constructed as a prefix SOR on the same range. So those two are equal, those two are equal, and so on. And maybe the last pair is split. So in this case, so okay, for all the pairs that are fully inside my prefix, their contribution is 0. So like XOR 0, 0, 0, 0. And maybe I need to know this element. So my value is either just this prefix SOR, which I know, I can calculate, or it is prefix this prefix SOR XOR this element. But this element has position x over 2, so I can like continue. But basically, I can make a recursive call, but instead of doing actual recursive call, I will just like write a while loop that will basically I just need to do the same but with x halved and then XORed by some constant, but I can just like keep the XOR of those constants in the variable and then just XOR the answer by it. Okay, so now I can implement f in all of log. See, because the number of iterations in that loop will be log c, because each time I have my number. Okay, now how to solve the hard problem. We will try to do more or less the same thing. So again, recursive functions that will find the answer to the problem, the sum on this segment. And to do that, This is actually not that simple, but okay, let's see. So here's our segment. If that segment intersects like with prefix of length n, I can add the suffix sum by hand and move left border to n. So now I'm considering that L is at least n. And again, I have those pairs of equal elements, except maybe the first element and the last element, but maybe not, depending on the parity of L and R. So now for the like those potential border elements, I will just call function f and like find them by hand and add to answer. Okay, now for those pairs of equal elements, I kind of want to say that I want to find the sum of those elements and then multiply them by 2. And for each of those elements, like their value is like how we discussed here, it's prefix or here and then maybe XORed with this element if it is on odd position. Okay, I don't like that. Am I stupid or is this contest hard? Okay, it should be doable. Yeah, so like my idea was to say that like okay, those elements are split into pairs, so like find the sum of all the elements and multiply by 2. Then every element is like count like this, which is like either just this prefix or so. Okay, let's call the prefix or C. So it's either just equal to C for like, certain parity, and it is equal to C XOR the corresponding element like on position x over 2 for the other parity, such that this element is the first in pair. And so now I need to find the sum of those like first in pair elements. But that's basically what I did here, right? So basically all the elements like elements in each pair are equal, so the sum of the first elements in pair is just sum on the whole segment divided by 2. So if I'm super careful, I should be able to like construct the right recursive call. I might also need to XOR them with value C, which is either 0 or 1. If it's 0, just do nothing. If it's 1, I have values that are zeros and ones, and I need to flip all of them, so the sum is just the count of them minus the sum that was before that. So, that should be possible to do, but I don't like that. Let's look at the other problems. In problem E, actually by points d1 plus d2 is equal to f, right? So like, d2 is supposed to be hard. Okay. Problem E, you're given a tree. Over time, each vertex I has a probability given of falling. Determine the expected value of the number of unordered pairs of distinct vertices that become leaves in the resulting forest. Okay, so we're given a tree. Each vertex has a probability with which we erase it. A leaf is a vertex that is connected to exactly one edge. So if we have a forest of one vertex, it is not a leaf. We can easily calculate for every vertex the probability that it will become a leaf. It's like the vertex itself should stay, and also exactly one of its neighbors should stay. But those events are not exactly independent. Number of... Okay, let's say that we fix a pair of vertices want to be leaves. We can actually like fix directed edges that we want to point to two different leaves. There are like 3 big options. First one is, well, obviously they can be like all independent. Second one is that this parent is a common parent for V and U. And there is a third option when V and U are actually each other's parents. So we have a component of size 2. It shouldn't be like super hard to count the sum of probabilities like over everything that this exact thing happens. But it's also might be a bit cumbersome because like there are a lot of things. I mean, even the number of these options is like potentially quadratic. Like if we have a vertex with big degree, then the number of ways to choose 2 different vertices from it is quadratic. There are also some bad cases that we don't like, right? There can be case like this, and case like this. Yeah, both of them just bad, because this is not a leaf, this is not a leaf. But we need to be careful to not calculate them. This is just great. I don't like this problem either. Let's look at F. 6 seconds. I already don't like this problem. Array v1 bm of length m is called p towering if there exists an index I such that for every index j the following condition holds: bj is at least p minus I minus j. So like we drew like this scene with point at ip, and the array must be higher than it. Okay. Given an array A of length n, you can remove at most k elements from it, determine the maximum value of p for which the remaining array can be made p towering. At most k elements. It's actually not always good to remove elements. But it's always good. It's always good to take elements. Okay. So I want to draw a scene like this. It will point at some of the original elements, and then like I choose subsequence to the left, subsequence to the right. Well, I clearly want to start with binary search and answer P, and then check if I can achieve that. Let's also say that I'm choosing which element will be like this position. So fix P with binary search and fix I. Now, like, left and right parts are independent, and basically I want to run from right to left, starting from I, and if I can take the next element, I want to take it. So it's like very simple greedy, and that's like n square log, because so this is log, then I fix I, and then I have like linear greedy. I guess I want to like optimize the linear greedy part with some data structures, or maybe like calculate them together somehow for different I, maybe even for different P. I don't know. I think some scanline with segment tree should work. Like, left and right parts are independent, so I want to solve all the left parts from left to right, and then all the right parts from right to left. Like, find the answers for every I, check if at least one of them is good, make the necessary step in the binary search. What happens like when I want to solve like this thing? So basically, when I look at the element, if it is at least P, then it's already good, I can always take it. If it is smaller than P, so like, say that the element is like here, to take it, like when I will run from right to left, if I want to take it, it means that I need to like take at least this many elements before that on the right. So when I will run from I to the left, I will take some elements, and if I took enough elements before reaching this one, I will be able to take it. Otherwise, I will not be able to take it. And so I can remember that information like that. For this element, I need like k more taken on the right. So now I'm moving this element from left to right, and maybe at some point like I want to take another element because it was already big enough, like bigger than P. I'm saying, okay, I can take it, so for all the previous elements, like I took another one, so I kind of decrease their like what they want by one. And if some element went like 0 or below 0, so they don't want anything anymore, so now I can take it. So I'm like, okay, I am taking it, and so I need to again decrease all the like wanting values to the left of it. So I can have a segment tree in which I will store what each element wants, and when I take some element, I do -1 on the prefix before that element. Then I can take minimum of the values that I have now, and if minimum of them is below 0 or equal to 0, I'm saying, okay, so for this element it is satisfied now, its condition was satisfied, so I can take it. So I will set this value to infinity so that I cannot take it anymore like the second time, and do the -1 on its prefix, and so on. So I have the segment tree. Since I take each element only once, like at most once, so like the number of operations with the segment tree will be linear. And that's it. Just do this scanline. So the whole solution is do binary search on P. Then for every P, like for fixed value of P, now for every I want to like understand what is the maximum number of elements I will take if I put this one at the top of this mountain. This can be done by greedy, by running from it to the left and from it to the right, and just greedily taking each element if it is already satisfied. Now I'm saying, okay, I will do left and right parts separately, and I will first do all the left parts together for all I, and then all the right parts together in the same way. Now, when I'm doing all the left parts, I will do them like while moving I from left to right. For each element, I want to remember like when I will be able to take it. Maybe I can take it right away if it is big enough. If it's not, then I need to take some elements on the right, and I will remember. So like I can take this element if I take some k on the right. Those values I'm storing in segment 3. When I take something, I decrease all the conditions that are left by 1. If some of them go below 0, so they are satisfied now, so now I can take this element. And I will be able to take it if I move even further to the right. So do this. It will be O of n operations with segment 3. So n log n for one iteration of binary search, and n log square altogether. Okay, this I can write. Not that hard even. Especially considering I should have a segment tree. I guess I will need to modify it somewhat significantly. Or no, actually, it's good, right? So this is add on segment, and this is minimum and position of minimum. And I have add on segment and set on point. Great, I don't need to do anything. Everything was done by Umning before me. That is great. Very grateful to that guy. So solve of x will return what is the maximum number of elements I can have if I want the top to be x, and if it is at least n minus k, so I'm removing at most k elements, then it is a good value, otherwise it is a bad value. So the answer is the biggest good value. The element on the top should be at least x. So if it is, then I can take it surely, otherwise I cannot take anything. So if I is the top, then I already did what everything I could have done, so just add core answer. And then if it is not the top, if it is at least x, then I can just take it, or I should put it in the segment tree, but actually I can just put it in the segment tree in any case, and then do the while true I need to do. So okay, set point x minus ai on position I want to set val with this. Okay, so this is like how many numbers on the right I still need to be able to take this value, and it is just this position of this value. Now while true, I will look if there is someone who is satisfied, take it and like activate it and replace it with infinity and subtract 1 on the prefix. So actually I can just look at tree of 1. If the value is positive, means that no one is satisfied, so I just break. Otherwise its position is p core ans plus plus set point at position p val infinity. I cannot take it a second time. And also at segment on the segment from 0 to p as the update -1. That's now do the same thing from right to left. change else. Okay, I need to add on suffix now. Great. Interesting. It's almost always one less than what they say. Alright, the first taken also counts, so I guess it's one less here. So yeah, the top of the mountain also counts as like counts towards satisfying the limits for others, so I should decrease it by 1. Okay, so well, this should work, and I have 20 more minutes, so I can try to, well, at least do D1. Well, D1 should be like without any issues, and D2 I think I can do also in 20 minutes, so let's try to do that. I will try to write the code that it will not require any changes for D2 in the easier part, but I will submit D1 when I can, because like for D2 I still need the function that just counts one element, so I will write it first. It's interesting. I thought there are queries. I don't think it will help me in any way that there is only one query, but I think that like I answer the sum on segment in just log squared of C, so I could have answered like 100,000 queries, but there are like a lot of tests, but for the same string I could have answered like a lot of tests, I think. You and series in 6 seconds. Oh, excuse me, but it's like analog squared in 6 seconds. It's not even heavy analog squared. So maybe I have some bugs that make it not analog square. How can it not pass in 6 seconds? No, that's insane. So this is Loxy. I don't get it. I can do like like that. Okay, let's make like slightly less variations signal. But it cannot be terrible. Something is wrong. I cannot see it. There aren't any clonks, module operations, so this shouldn't be a problem. I just don't get it. And now I have broken it. Great. Right, because yeah, copy paste is bad, children. 6 seconds. $200,000. It should work less than a second. So maybe two. Cannot be more than that. So I guess something is just wrong. 10 to the 9s. But my inf is 10 to the 9s. But that shouldn't matter, right? I only like decrease it by 1. Like I made it slightly faster, maybe 2 times faster, but that's like on a good day. I don't know, something seriously wrong. But I cannot see it. How? How is it so slow? Okay, whatever. Let's just try to write Div1. Well, for Div1 I don't need pref sum. I don't like. Okay, if I'm just writing Div1, it's, if I'm just writing Div1, I just want n to be odd. It's plus an is prefixor of n over 2, and prefixor of n is prefixor of n minus 1 xor an. Great. So if it is small, then good. Otherwise, okay, and now n is odd, then even odd are the same. So if x is even, we need to XOR it with f of x. What? A third failed? Oh, I probably need to read n, right? Okay, that was a very bad contest for me. But mostly because I just didn't want to write some problems. I mean, D2 should not be that much harder. And E, no, I don't want to do that at all. And F is super easy. 20. Sure, okay. But why is it so slow is just baffling. Okay. Yeah, that was kind of bad. But maybe educational. Yeah, we are not gods. Sometimes just the contest just goes wrong. That's fine. Thanks for watching. Bye.